Okay, so it's time to begin now, and I just want to let you know that you should check your current grade. That's without the bonus right now on Compass. And also, I really encourage you to come and pick up your exam because you not only get your exam, but you get your error sheets. I can show you that, show you what you got wrong and what the correct answer was, and go over it with you. And so that's pretty much it, and let's go to the document camera right away. And we're going to start on page 141 today. It was the last page in chapter 29 here. And we were talking about interaction terms and confounders, and they're both pretty complicated, and I thought a visual might help you show you how they differ. They're not the same thing. So hopefully this will make sense to you. So what is an interaction? Let's start with that. So if you have two groups, like a group A and group B, you can see group A and group B. What an interaction term is when they're different slopes. Like, for example, let's look at this. So do you see within these two groups, neither one of them, they both have flat slopes here. Whereas here, they both have, you can see the slopes there. And here, this group has a slope this way, and this group has a slope that way. And here's the slopes there. Now, looking at these plots, let's label them 1, 2, 3, and 4. I'm going to ask you this eye-clicker question. Which plots have an interaction? And I'm also going to ask you which plots have confounders, a confounder. Let's start with the interaction right now, and let's look at this. And let's go over here. Okay, so let's start this right here. Whoops, you can't see that. It got cut off. Darn. Shoot. Let me try to get that back. What does it say? It says only plots. This one says only plots 1 and 2, and this one says only plots 3 and 4. Sorry that got cut off. So that's 1 and 2, and that's 3 and 4. I can't move it over. So if you just came in here, we're asking which plots have interactions here, and all of them? Do you think all of them have interactions? Do you think none of them? Do you think only plots 1 and 2 have interactions, or 3 and 4? Or all except plot 2? Those are your choices. So just pick one if you're just getting here now. And let's stop it and see what you said. Okay. Let's see what you said. Great. It's D. And so only plots 3 and 4. Why? Because you can see there 3 and 4 have different group slopes. You see, these have the same group slopes, but plots 3 and 4, these two, they're different between the two groups here. Does everybody understand that? You have a question?
Yeah. So the interaction in plot, or there's no interaction in plot 1, the slopes are the same.
Yeah. Mm-hmm. We're looking at the effect. Okay, so here's the X and here's the Y, and you have two groups here. And we're saying, okay, do the two groups, have the same slope or not? And these, when they have the same slope, there's no interaction. And interaction means that the two groups have different slopes. You got that? Okay, so the answer is 3 and 4. Now, this is going to be a hard one, but let's see if you can get this. We might as well try it. I'm going to ask here, which plots have confounders? So I just want you to, I don't expect you to get it right away, but just see if you can figure it out. An interaction, remember, has an overall slope. Here's your overall slope, right? That's different than the average of the two group slopes. Here's an overall slope. So you're going to have to picture this. Just, I don't expect, just what your intuition says, and then we'll look at it. Which plots do you think have confounders? Where the overall slope, like this overall slope, like right here would be the overall slope, here would be an overall slope, is confounded by group membership. So just pick, a choice here. Okay, and I'm going to stop it and see what you said. The answer here is C. Let's see if you got that. No, you didn't quite get that. So, okay, so we're going to go over that. Why don't we go over that? Let's go to the document camera, and let's answer these questions and go over. Okay, so which plots have the interaction? This was only 3 and 4. Right? Because you could see these are the only ones that have different group slopes. Different group slopes. Now, which ones have confounders? And the answer is only 1 and 4. And let's think about why. We didn't really go over this, so I didn't expect you to get it right. First of all, so let's look down here, and it says interactions are different slopes within groups. Now, confounding says both these conditions must be met. Different x averages for the two groups, and that the overall slope is different than the weighted average for the two groups. So let's draw them in. What's the overall slope for this? So the overall slope, do you see what's the overall slope is going to look like this, because the regression, if we actually did a regression, it would pretty much see these as 2 points almost, and draw the overall slope would look like as x gets bigger, so does y. You have this overall slope here, which is really deceiving. It's confounded, because neither one of these groups, it's saying there's a positive slope between x and y. As x grows, so does y. But that's not true of this group or that group. And in fact, what's true, if you sort of average the two groups, the weighted average of the two groups is something like this. So that is an example of confounding. It has different overall than weighted average. And when that's true, you're also going to have different x averages for the two groups. So you can see they have different x's. The x average for this group is right here, and the x average for this group. So that's one is confounded. Does everybody understand that? Because if you look at this, you're not going to get this. If you did a regression, what would appear is just this yellow line. And you'd say, you could conclude if you didn't look carefully, that as x increases, so does y, but it's not true for anybody. So that's why it's bogus, yeah?
Can you explain why number 3 wouldn't be a confounder?
For the interaction, why this is an interaction?
Or why it wouldn't be a confounder?
Why this wouldn't be a confounder? Great. Well, first of all, it doesn't have different x averages for the two groups, so it couldn't be a confounder. But that really is a consequence of this one. When this is true, when 2 is true, 1 always follows. I just wrote them there so you can get a visual. So you can right away know, but why is that? Okay, so let's look at this. So we're looking at what would be the overall. The overall is what the regression analysis would say, okay, basically, as you go as x gets bigger, what you can't, this is the overall. You can't it's just seeing it as just, there's no overall pattern here. Does that make sense? And that's exactly the same as the weighted average of the two groups. Does that make sense to you? Okay, so that fails both conditions, but this is just, whenever it has different x averages, it can't have confounding. Because confounding, let's just take a look at what confounding means. It's if we're talking about the group being a confounder, that means it has to lead to what? Basically different x's, and it's going to have to affect y too. It's not x affecting y, it's really the group affecting both. Okay, so now let's look at this one. So this one you can see, I think you can see why it doesn't have confounding. The overall is just like this, and that's the same as it's the same thing as the weighted groups. Now this one, I think you could see that it has confounding, because look at this. The regression is going to look at this and say, okay, as x increases, so does y. It's going to give you a regression line kind of like that. Whereas it's completely bogus, because here it has a negative correlation within this group and nothing within this group. So the weighted average should be some halfway between those two slopes, something like that. So this certainly has both. 4 has both. It has interactions. So this is both. 2, it doesn't. 2 has. 4 has both. 2 doesn't have an interaction or a confounder, so this is neither. And 1 is only confounding. And 3, right here, is only an interaction. That's kind of a, here, let me go wide on this. Sorry. I'm trying to fit everything in here. That was kind of a very difficult question, I think, but I don't know if it helps clarify anything or not, but I think you have to see this a bunch of different times. Any questions on it? Okay, and let's move to the next. So here's the summary here on the next page. This is the end of chapter 29. And so a linear model with just main effects has no multiplicative terms, no interactions. Okay, and these terms can be categorical or quantitative. They're called the main effects. But then if you have an interaction effect, that's a multiplicative effect, and it changes the effect on of one of the variables on y changes depending on the value of the other variable. So it causes the slopes to change. So if you think that the slopes changes depending on, in the examples we gave you, the slope changed depending on whether the x2 variable, let's say that was group membership, was 0 or 1. And so let's see. So basically, when we were doing, this was last time we looked at, when we looked at an additive model here, we saw how when we add this gender term right here, the coefficient, this, gender was just 0 or 1, so that allowed for different intercepts. But we had the same slope. So here, this showed that the intercepts differ by that amount. So this would be the difference in intercepts between the two groups. But they have the same slopes without an interaction term. See, this is, without an interaction term, you're going to get the same slopes for these two groups. But here, when you add an interaction term, here, this is still the difference in intercepts right here. But this right here, this multiplicative term, allowed the slopes to change because it was a 0, 1 term. So when gender was 0, this was the slope, but when gender was 1, you had to add that to it or subtract that. So that's the difference in slopes. So this is pretty easy to see when you have a 0, 1 variable. At the end of the hour, we're going to look at two quantitative predictor variables, and that will be, it's more difficult to see. So we're starting off in this very simple case where we're adding just this binary variable. And we're going to look at interactions next in an even simpler case where we have two binary predictors, which is the very interaction terms in the simplest settings. This is often the easiest way for you to understand an interaction effect, because we're just going to look at two 0, 1 variables, two binary predictors, and that's the very simplest case, and we can graph it pretty easily. So here's an example. It's also, so we're going to have a quantitative response variable, a quantitative y variable. This would be our quantitative y. We're going to look at duration of disease, how long some disease lasts, and based on, and then to see how drug A and drug B affect that. Okay, so drug A could be X1, whether people take it or not. It's a binary variable, and whether you take drug B. And I'm sure you've heard drugs, when drugs have an interaction, they say don't take this drug with another drug, because even though taking either one alone might not be harmful, together they might be. That would be an interaction where something is different than the sum of its parts. It could be better or worse. It's a synergistic effect. All right, so let's look at this. So drug A is coded either 0 if it's given, or 1, if it's not given, and 1 if it's given, and same with drug B here. And so here's an example of no interaction effect whatsoever. And so without any drugs, your disease lasts 10 days, and then if you take drug, it goes down by 4, minus 4. When drug B is 0, you're not even, just the effect of drug A is minus 4. Then the effect of drug B is minus 2. That brings it down to 8. And then if you take both of them together, it's just an additive effect. 4 minus 2, and you get 4. And the picture would be very simple. This is no interaction. The drugs don't interact. They're just the sum of their parts. And if you wanted to graph it, you can't graph all three variables in a plane, right? You can only graph, so I'll have the y, and I'll do here, drug A goes from 0 to 1, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so what it's saying is if you don't take any drug, when A is 0 and B is 0, then you're at 10. If you add A, that's right here, to 1, you're going to get to 6. 1, 2, 3, 4, 5, 6. So right there. So that's when B equals 0. Okay? I can't, in 3D, B would be up here. It'd be coming out, but I'm just drawing it here. B equals 0. So what happens when B is equal to 1, when B is equal to 1 here, so now, when A is 0, right, and B equals 1, it lasts 8 days, right? So that's 8. And then if you give them both, it lasts 4 days. So it just has the same slope. It goes down 2, it goes down to 4. And this is when B equals 1. Okay? So those are those parallel slopes, no interaction term. Now I have two interactions. Here is when the effect of the two drugs combined is better than their sum. This is a bad thing this lowers it to, okay, so when you have, looks exactly the same, but instead of 4 here, instead of having a 4 here, what should I put here? It's saying we're going to subtract when you have both a 1 for both of these. So you put a 1 in here, times 1, and here's 1 times 1. I'll write it down here. So you have 10 minus 4, you have the presence of drug A, minus 2, the presence of drug B, and then it has this interaction effect where it even helps you more. And now your disease only lasts 1 day. So it has a synergistic effect. The sum is, they help each other, the two drugs. They're more than the sum of their parts. Okay, so the picture would be the same except for the first. Okay, so let's draw the picture. Okay, so now you have 0 and 1. Again, this is A, and this goes up to 10. Right here, Y. And it goes down to 6, right? When B is equal to 0, it goes down to 6, right? But now, and again, when A is equal to 0 here, you still have this 8. But when you have the two of them together, it's going to go all the way down to 1. So this is no longer parallel. Okay? This goes down, it basically goes down 3 right here. That's what it's telling you. That it's adding an additional effect of 3. So that's what it looks like, non-parallel slopes. That's when B equals 1. So what changes is when they're both together at this point, 1, 1. So here's the same thing, but now it's going to be worse. The effect of is worse than the sum of their individual effects. It's worse because now your drug is going to last 7 days more. So here, watch, we can do the same thing. We have 10 minus 4 times 1. I'm putting 1 in for everything. Minus 2 times 1 plus 7 times 1 times 1. So now we have 11 here. It's 7 more than what it would be before. Okay? So we'll draw the picture. And this is going to jump up to, we'll have non-parallel slopes, and when both of them together, your disease is going to last longer. We'll go way up there so we can draw the picture again. So this is all the way up to 10, and it's going to go down to 6. See? And we'll start off at 8, but now it's going to go up to 11. It goes up all the way there to 11. And that's when B is equal to 1 and A is equal to 1. And of course, this is still B equal to 0. So that's the idea. So these two have non-parallel slopes, and that's what the interaction effect does. It allows for different slopes. Okay? So now on the next page, what we're going to do is we're just going to match these models, this really simple model, with the data. And let me show you, or if you're finished copying this down, let's go here. And let's look at this example. So suppose A and B are two treatments that are designed to boost scores on some exam. Coded 1 if given, 0 if not. The numbers in the table indicate the average boost from each treatment by itself, from both together, and from neither. Fill in the blanks below so the model and data match. Okay, so this has no interaction, right? No interaction. So what's it saying? The blank here is just putting in a 1 for A and a 1 for B, and you get 50. Okay? And you can see that this is very, very simple, and there's no interaction here. Now let's do the same thing, but we add an interaction term. So here, now when both drugs are given, you create an additional boost. You can see you go from 50 to 60. So it's a boost of 10. You can see that, and you could easily see it just by plugging this slot right here has a 1 for both of them. So you just say 20 times 1 plus 30 times 1 plus what times 1 times 1 is going to give you 60, and that's 10. Okay. So now for here, let's look at this. So here you're given this data here, and now you want to come up with the model, the formula. So the easiest way to start is, okay, so this says when A is 0 and B is 0, what's the boost? That means that without the drug, maybe if you take one exam, then you take it again, you just get some boost without any drugs, right? So that would be 2 right there. That's the starting point. Then if you add drug A, going from B still 0, so if you add drug A, that will give you a boost of what? 6. And what does drug B give you? When A is 0, what does drug B give you? 2 plus what? 8. So that's 8. Okay? There's no interaction there. So if there's no interaction there, you're just getting the boost from both of them, so it's 2 plus 6 plus 8, which is 16. And you can see the parallel slopes, because if you started here, you could add 8 and get 16, or if you started here, you could get 10 plus 6 is 16. You have this same slope. So this last, why don't you try to fill in some, why don't you see if you can fill in some of the rest of it. It's probably better. I'll just give you a few minutes, talk to each other, and see if you can fill the rest of it in. Because I think we're right on track to finish this lecture. So I can give you some minutes to do that. And that'll make your homework easier too. I think you have something like that for your homework. And feel free to talk to each other and share with each other if you have a question. Okay, look up when you're finished. I'll give you another minute. Okay, so I did these two for you. I just put ones in here and you get 55 for that one. And for this one, you could see that the coefficient, this says, as you go in front of B, you add 30 here. And then what I did was, if you can just follow the directions here. This says when B equals 1 and A equals 0. So you put it, if you want to, you could put a 0 in for A and a 1 in for B. That would give you, and that's going to be your result. Now to get this one, it says put a 1 in for both A and B. That's 1 times 1 is 1, and you just get 20 plus 30 minus 10. Every questions on that? So let's do this one together. So this one says what? When A and B are both 0, that's 10 right there. And now it says, as you go here, B is 0 throughout this whole line, so just forget that. It says 10 plus 2 equals 12. So that's how you'll get that 12. And now when you go down here, this says A is 0. So just blank those out and you say 10 plus what will give you 15? And that's 5. So this is 10 plus 2 equals 12. 10 plus 5 equals 15. So that's how you get that. And then this interaction term, how do you get that? Well, you just say 10 plus 2 plus 5 plus what is going to equal 9. And so that has to be what? Negative 8. And what it's saying is, look, this drug is great. This drug is good. It boosts you up to 12 points more, 15 points more. But then if you take both of them, you're worse than if you took nothing. You go down. If you took nothing, you're at 10. You go down to 9. And here it says the term is better than the sum of the two effects. Okay? So here you got 12, 15, and 20. So this is the same exact thing, 10, 2, and 5. But now it boosts you up by what? Well, you say 10 plus 2 plus 5 plus what equals 20, and that's 3. Okay, so that's the idea. And these are kind of pretty simple. And it gives you a good feel for what an interaction term is in its simplest setting. So now we're going to get to the hard part where we have two quantitative x's. And that's more complicated. Okay, so let's look at that. So this is part 11 here, multiple regression with quantitative x's. We're going to start with 2 so we can visualize it, and then we're going to move towards more than 2 and combine quantitative and, categorical ones. Okay, so remember in simple regression, when we draw a scatter plot, it's a line, right? And that's our model. Looks like the predicted y equals some intercept plus a slope times x1. But now let's say we have 2 quantitative variables. Then our regression equation looks like this, even if we had 2. This is just 2 predictor explanatory variables. But we're going to look at the case where they're both quantitative now, and it's of this form. And so what we're going to do is we're going to expand on that example that we've been looking at with 100, it's called the grades in the data set, and it looks at the exams and homework averages predicting finals of 107 Stat 100 students from a while ago. So these, I'm going to, I actually copied this down wrong, 81.82. If you want to make that correction, that's what the homework average was. And this is the same example we saw on page 116 in the notes and page 131. Okay? Where we looked at the simple regression equation of exams predicting final and homework predicting final. But now we're going to look at putting them together, exams and homework together predicting finals. Okay, now the first thing you might notice is there's this correlation coefficient that's a capital R. So what is this multiple correlation coefficient? We've talked about it before, and we said that it's the absolute value of that R. The multiple is the abs for simple regression. It's just the positive value of our regular correlation coefficient. So for simple regression, remember, do you remember what the correlation coefficient is between just an x and a y? You change the x and y to z-scores, you take their product, and it's the average of their products. And then, R can go be range between -1 and +1. Now, what do we do with multiple regression when we have more than two variables? More than two variables. Well, correlation's only defined on two variables. It's two sets of numbers. You can't really have three sets of numbers or four sets of numbers. It's not defined on more than two sets of numbers. So when we go to multiple regression, what are going to be our two sets of numbers? So for multiple regression, it's going to be the correlation between these two sets of numbers, which is your actual y values and your predicted y values from your fitted multiple regression equation. Okay, that's what it is. It's the average of the z-scores between, we can write this down here, so it's an important point. Correlation is only defined on two sets of numbers. Or two variables. So the correlation in multiple regression, so where you have three variables, what do? You need to get two variables. So so for multiple regression, you have to do something different. This capital R, which can only be positive, is the correlation between two sets of numbers, and what are they? Between your actual y values, like in this case it would be the actual final scores the students got, and the predicted finals from our regression equation, the predicted y values. Okay, we call those y hat. So the actual y's and the predicted y values. And it's the sum, so R is equal to the sum of, what do? You change those both to z-scores. These are your actual y's, and these are your predicted y's. So it's still the product of the z-scores, the average. You sum those all up and divide by however many there are. But now, R can only be positive. Why? Well, think about it. If it's the correlation between your predicted and your actual, you want them to be close to each other. So even if there's a negative correlation, like x could be, as x could be the opposite of y. It could be, as x gets larger, y would get smaller if it's a negative correlation. But our predicted y's would always be of the same, get closer to your y value. So it's always going to be, it's not going to be a negative correlation. It's going to always be a positive correlation here. So it would be between 0 and 1. And remember, that's for multiple regression. For simple regression, we have little r, and that's defined as just for z between x and y over the product, cx, this is the sum, the sum from I equals 1 to n, however many pairs you have, of zx times zy divided by n. So it's the average of their products. We did this. And here, for simple regression, r is equal to the absolute value of r. So you could do it this way for simple regression, but it's always positive. Excuse me, I wrote that wrong. The r is equal to the absolute value of the little r. The little r can range between what? Little r can be between 1 and -1. That's little r. But big R can only be positive. So You could do it the same exact way as this for simple regression, and you'd get the absolute value of R. Okay? Any questions on that? Okay, so now let's look at what this looks like. So let's look at what this looks like in 3D. So in 3D space, because now we have, we're no longer aligned, right? We are in 3D space. And so here's the homework, here's the exams, and here's the final. And what we're doing now is we have a multiple regression equation, and this is what the computer gave me, and we can look at it. So it has y is equal to some intercept plus x1 plus x2. It's the best fitting what? Let's do this as an iClicker right now. So choose between, what do you think this is? This is the equation of what? Do you think it's a line, plane, ellipsoid, cube, what? This equation right here. And so let's just go to our, here. And start this. Okay, let's see what you said. Stop this. And it's the best fitting plane. Great. Now let's look at, let's go back to the document camera for a minute. And what this is showing, look at this. It says, given, what we're doing here is given people's homework and exam scores, we're estimating their final scores. So the scatter plot shows the final exam scores. These are as a distance from their point in the homework exam plane. So this is see all these dots here? Now what we're trying to find is the best fitting plane through these points. We're not going to, obviously we're not going to hit all of them, but we want the best fitting one to do what? To minimize the sum of the squared errors in what? That's your next iClicker question. It's the best fitting plane through there to do what? So let's go to the PC. And that's your next question. Okay, I'm going to stop it in 3 seconds. So, all right, let's see. Its final score is C. Great. So now let's write that down. And so it's the best fitting plane through all the y's so as to minimize the squared errors in the finals. So let's look at the next page. And here's a picture of the plane. You can see it. It's the plane that minimizes the sum of the squared errors in the finals. The errors, you see, this has a big error. See that? That person was expected to get a much lower score, and look how high that error is. But you can't hit them all, so that was a big residual. But this plane, if you can see this plane, maybe you can see it better if I show you. This right here, it's this plane, so look at this part right here. this is the homework slope. And it's more gradual because homework isn't as good a predictor as the exams. And this right here, the tilt here, is the tilt of the exams, which is much bigger. See how the homework is the tilt of the plane as you go from 30 to 100 on the homework? And this one is much steeper. We can compare tilts because all the variables are expressed in the same units. Otherwise, it would be hard to. So that's the idea, and that's the picture. So now we're going to look at where these slopes come from, because they're not the same as the slopes in the simple regression. As the slope for homework alone predicting final and exams alone predicting final. So we're going to look at how we arrive at these slopes in the multiple regression equation. That's what we'll do next. So slopes in the multiple regression model. One thing you'll notice, very important, is that the slopes are not the same as those in the simple regression, except when the predictor variables are uncorrelated. Let's look at this. As we said before, that the capital R, right here, we just defined it, is the correlation between the final scores, the predicted ones, and the actual. That's what we said. But now there's also these three little r's, which are the correlation. They're not the same as this one. They're the correlation between, this is R between Y and X1. This is R between Y, the final, and the exams, X2. And then there's the correlation between the two predictor variables, X1 and X2. So we have these three. And when these are correlated, like homework and exams are, these slopes aren't going to be the same. So let's look at the two predictor variables separately. This is X1, homework, predicting Y, final. This is homework, predicting final. And this right here, exams are X2, predicting Y, the final. All right, and you get two different equations. And what I'm saying is that these slopes right here, this is X1, and we'll say this is for the exam, are not the same as these down here in the multiple regression. See how it went down? The homework slope went down, and so did the exam slope. And they're always going to change if this correlation between homework and exams is non-zero. Now let's look at this. We see that both scatter plots have a positive trend, and that's no surprise. You'd expect homework to be, a good predictor of finals, and you'd expect exam average to be an even better predictor of finals. So that's no surprise that we have those. What do we gain by doing a multiple regression? Well, obviously, we can better predict final exam if we combine information from two predictions. But we could look at them separately. What do you gain by putting them together? We can also, you'll also be able to separate out the effects of the two. You'll be able to look at the effect of each predictor variable while controlling for the other predictor, keeping the other predictor constant. We get a different coefficient when we control for the other predictor. Okay? So what does that even mean? It means that, like, when you hear, you're saying, okay, I'm predicting exams, I'm predicting final from exams, ignoring homework scores. But people who have higher exams also have higher homework. So part of this effect is due to homework. Same here. And this, when we do this, we separate out the two effects so that we say, okay, for people who have the same exam score, let's say exam score of 80, then each additional point of homework increases their final by 0.1641. Whereas here it said, each additional point on their homework increases their final on the average of 0.3436, but some of that is due to the exams. So this separates it out. In other words, what this does is it says, okay, after I've already predicted people's finals from their exams, how much additional help does the homework do? How much additional help does it do? So let's write some of this down. So notice right here that the slopes have changed. They both got smaller. These got smaller from up here. Notice slopes have changed. And they always will change. But in this case, they both got smaller. Sometimes they'll get bigger. Sometimes one will get bigger, the other will get smaller. Sometimes it's hard to predict. Okay, and so why do they change? Well, the slopes change whenever the two, excuse me, can you see here? Whenever the two predictor variables, like exams and homework, are correlated. So whenever r between the two x's is not equal to 0. And I think the best picture is to think of it this way. When they're correlated, that means you can think of them, let's look at the, so you have, let's say you have homework, x1, and you have exams, x2, but they're not separate from each other. In the simple regression, some of the slope, some of this slope, the 3.3436, is actually due to the effect of exams and vice versa. So you can think of them as sort of an overlap with this part here. And they're both predicting y. So you don't want to double count them, basically. The effective, so these are actually called the partial slopes. These are the part of the slope for homework, the part of the homework, and the part of the exam that quantifies the effect of these variables on y after controlling for each other. So after you've put exams in the model, how much more does homework help, and vice versa. So these are called partial slopes, and you can see that's why they change. So these are called, in multiple regression, these are called the partial slopes, because they explain the effect of the x variable, the quantitative effect, after the other one has been partialed out or controlled for. It's just the language that's used, and it's helpful to see. So in this case, they get smaller because there's a positive correlation between all three variables up here. All right, now I'm going to ask you an iClicker question that the slopes change when this is true, but when are the slopes, when would they not change? So let's look at that. So we'll go to the next one. Okay, I'll give you a few more seconds and then we'll stop it. All right, and the answer is when the correlation between them is 0. And let's draw the picture and I think you'll understand why. So let's go back to the document camera and write that down. And the slopes stay the same when the correlation between the two predictor variables is 0. So the picture is this. Knowing there's no correlation between them, they're completely separate. So this is like, let's say x1 was height or something like that, and x2 was exam score, something really that are uncorrelated, and they might both have an effect for some reason on your final exam scores on y, but they're separate. So in the simple, they don't have any correlation between the two of them, so that when you combine them into the multiple regression, they'd be the same. So if there was no correlation between homework and exams, these two slopes would just remain the same. They wouldn't be, because there's no correlation, so when you control for one of them, they wouldn't change because they have nothing to do with each other. All right, you got that. Now, all right. So let's look more carefully at this. And do we have the same slopes? I'm just repeating myself in the multiple regression as we did. No, we don't. And why did they change? Because they were correlated. Okay? They change because they take into account how they're correlated. Okay, so now you can, something that's always important to look at in any multiple regression analysis is the correlation matrix. So this is called a correlation matrix here, and it shows the correlations between the variables. So here is x1, x2, and y, and here's x1, x2, and y. And now, the first thing you might notice is this. In all correlation matrix, this diagonal along here is 1. Why? Why? Anybody know why that would always be 1? Yes? Exactly. Because what this is saying is a variable homework is correlated. If you know homework is perfectly correlated with homework, exams is perfectly correlated. Exams and finals perfectly correlated with finals. So why? Because a variable is correlated with itself. Has a perfect correlation. So R between X and X is equal to 1. Now the next thing you'll notice in all correlation matrix is the symmetry of the off diagonals. For example, this one and this one are the same. Those two are the same, equal. This right here, the off diagonal with this are the same, and this are the same. Why are they the same? So the off diagonal terms are always the same. Why? It's completely symmetrical. Do you know why that would be? Do you know why that would be? Because what? Anybody? Why do you think that's the same? What's this saying? This is saying, for example, that the correlation between homework and exams is the same as the correlation between exams and homework. Wouldn't it be the same? It doesn't matter. Isn't that the same? So it's because the correlation between X and Y is the same as the correlation between Y and X. Doesn't matter which way you write it. So that's something you'll always notice. Now, we've looked at the two plots here, homework predicting Y and exams predicting Y, right? These are two predictors. Now let's look at the plot at how homework and exams, the two X explanatory variables, are correlated. Let's look at this scatter plot. And this is between basically X1 and X2. Between homework and exams. And here's the equation for it. And how did they get this equation here? Well, this slope, which is what we want to focus on right now, this slope, remember, and you need to remember this, is r times s dy over s dx. So which r? Well, it's going to be r between the homework and exams. So there it is. And of course, okay, so that's what we're using right here, which is this. 0.3933, and then times the ratio of their standard deviations, which we can find on page 145, right here. So we're predicting exams, so it would be exams on top, would be y. So this would be 9.197 over 11.73, and that's from page 145. And that's how this slope right here was gotten. All right. And we're not going to worry too much about the intercept. So that's how we got that. And now what I'm going to do, it's unless you really know matrix algebra and know how to, you can solve for these slopes from the two separate simple regression equations by doing matrix algebra, and it's pretty simple once you know that. But since this is a course where it doesn't assume you know that, I'm going to show you a way that to at least go from here without matrix algebra. It's very easy to go from the multiple regression equation to the simple one, so that you can understand this better, where these terms come from. So that's what I'm looking at. So I'm going to show you how to do that. All right. So let's do that on the next page. Let me see if I covered everything I want to here. I think so. You should read all this, but I'm not going to read it for you. These are the partial slopes again. Right here, maybe I should say. Those are called the partial slopes. And I'm going to show you how to go from this partial slope to this slope that ignores exams. So let's do that. Okay, so now, how do we do this? All right, so we're going to start with this full model here. And I just want to show you how you can use this equation that we just got, this right here, to get to the simple model. All right? So we're going to start with this full model right here. And to get the simple model, we want to eliminate exams from the equation, right? We just have homework here. And just focus on homework. And we need to know how exams and homework are related. So here was the equation we just got. And all we're going to do is we're going to put this part of it, this, right here in for exams. Substitute that for exams. Of course, we'll change the intercept, but we're not worried about that. And then just see what we'll have. We'll have 0.1641. That's the partial slope. And then we'll have, when we substitute this in for here, we get 0.58240 times 0.3083. And that is the, right here, that's kind of the part of the homework that was mixed in with the exams. So then we have, here's the partial slope, plus the part of the homework that was actually captured by this exams, and that's how we add those two together, and we get that. And that's how it works. So we can do that here. I mean, here's just the words X, a longer, more detailed explanation of what I just showed you, what I just said. But here, why don't we do the exact same thing, but this time go from this, the multiple regression equation, to this simple one with exams. So now we want to eliminate homework from here. So let's just do that and all together. So step one is we want to eliminate that homework and replace it with homework expressed in terms of exams. So we want to express homework in terms of something times exams plus an intercept, which we're not worrying about. And so this is what we're going to put in for here. Okay? We're going to get some coefficient in there, and we'll put it in there, and then we'll have everything in terms of exams. But we need to get this equation. We just need to get that slope. And we just did it on the previous page when these were switched. So the slope, remember, is going to be r times s dy over s dx. So that's the same r we used before. It's the same r, right? But now, we've switched x and y, so we're just going to switch them here. Here, exams were y, now homework's y. So homework, SD will be on top. All right? So it's just going to be the same thing, but we'll flip those. So 0.3933, that's r. And now we're going to take the ratio of their standard deviations with the one for homework on top, which was bigger. And I got that. So that's what goes in here, 0.5016. And 0.5, can you see that? It's just a little over 0.5. Okay? So that's what's going to go. This right here, this expression, we'll go substitute in for homework, and then we'll have something just in terms of exams. Okay? So let's write what we have. So we have final is equal to the partial part, 1641 times the homework. But instead of homework, I'm going to write what? I want to get rid of the homework. So instead of that homework, I'm going to write 0.5016 times the exams. That. Right? .5016 times the exams. That plus what? 0.5824 times exams. So now this right here, when I multiply those two together, I get 0. What do I get? Half of that would be 0.8, right? 0.823 times exams plus 0.5824 times exams. And that's when I add those two together, I should get that. 0.6647 times the exams plus an intercept. It's really not hard, it's just the numbers have so many digits to them. All I did was just got rid of the homework, and I have this part. You know, here's the partial to the exams, plus here's a part of the exams that's part of this homework. About half of it was due to the exams. So we add that together, and then we get this. Any questions on that? You're not going to be doing much of this. You know, the slopes are hard to figure out. And so you're going to be, the computer is going to be giving you, we're just going to look at the slopes in the multiple regression equation. We're just going to let the computer do it for us. Okay? And we're just going to let software do that for us. Because it's hard to do without matrix algebra. But I just wanted to give you a feel for where it comes from. So I think you have a homework a question like this, but you probably won't have an exam question like this. Just because too many calculations, it's a little bit confusing. I want you to be able to do it on your homework, but the exam questions, you won't be so detailed. So now, yes, do you have a question? Yeah.
I think there's like matrix on the calculator.
What?
There's matrix on some calculators. You can't like use matrix.
I mean, I can show you how to do it if you want, but for those who have it, it's just inverting a matrix. It's very easy. But it's very easy if you just solve, it's very easy, but we don't, that's to come. That's if people go on in statistics. They'll see that in another course. But you know, this gives you a good idea. This gives you a nice conceptual idea of what's going on. And now let's just to sum up. Let's see what we want to remember here. Probably all of it, but something, okay. So this is important. The multiple regression assesses the effect of each predictor variable while controlling for the other ones. And this also, the slopes in the multiple regression equation are called partial slopes, since they quantify the effect of each x variable on the response variable after the other x's have been controlled for. Okay? How much additional information does that variable give after the other variable's been controlled for? And of course, this. When the x's are correlated, which they just about always are, those slopes change. Now, something we didn't talk about that's going to come up a lot is this: beware of multicollinearity. Highly correlated x variables. When you put two x variables in that are extremely correlated with each other, you can get very weird results because if they're almost the same, almost any linear combination of the two of them will give the same results. So you're going to get very bizarre results. Warning, if two predictor variables are highly correlated, don't put them both in the model. And the example I like to use is, imagine you know that your right foot size is a very good predictor of your height. But if you add the left foot size in, because they're so highly correlated, almost anything could happen. You could get, the regression program will fit the particular peculiarities of that particular data set you have, and you could end up with both of them being insignificant and only together being significant, or one dropping out or the other one. If you put them both in a model equating both in a multiple regression equation predicting height, either one or even both could end up non-significant. Because think of it this way: if the right foot size is in there, adding the left is not going to add any more information. It's just going to make it hard to fit with any linear combination of the two of them would do a pretty good job of predicting it. So it screws up your model. So that's really important to not do that. We'll see examples later on of that happening. Now, I think that's pretty much it and we'll start here next on Thursday. So I'll put some homework up that's due Tuesday for what the last part we covered.